Okay guys, so what I want you to do right now, we did the rubber band, the circles, and the book thickness graph yesterday. What I want to look at now is this multiple run graph.
Oh.
Okay, so the lab that we're going to do on Monday is going to work exactly like this. So like pay really close attention and you'll know exactly how to do everything on Monday's lab. Okay, because we're going to run a few carts along a track, okay, and we're going to kind of record how far they go, okay, and how long it takes them to do that, and they're all going to move at slightly different velocities, okay, it's going to be pretty simple, but we're going to graph them all together on the same graph, which means if I have 4 carts, I'm going to have how many lines? 4, okay, so all the graphs we've done so far, they were only 1 line, okay, because there was only 1 data set. Okay, now we're going to compare what it looks like when there's more than 1 data set. It doesn't really change anything. Okay? We still want to build the graph in the same way. So click and drag and highlight everything. Okay, same as we did yesterday. Insert your chart. Okay, but this is where you're going to run into Google not knowing what to pick. Okay, remember I told you yesterday that Google rarely picks the right kind of graph. Okay, I don't know whether this is like powered by AI and it just doesn't work very well. Okay, but it almost never picks the right graph when you have more than 1 data set. Okay, so it picked a column graph. I don't want that. Okay, that's not what I'm looking for. So I have to go here to chart type where it says column chart, and I just have to scroll down until I find scatter. That's what we were doing yesterday with scatter plot graphs. Click on scatter and I get the dots. Okay, same as I would have got yesterday for all the ones we did. All right, just yesterday it defaulted to that, it knew I wanted that or whatever. Okay, so now on this graph here that it's built, what's missing?
The line.
The lines, what else is missing?
The equations.
The equations, and what else?
Title.
Okay, the title sucks, yeah, we gotta get a different title, what else?
The name for the y-axis.
Right, the name for the y-axis. It doesn't, like Google, if you're only getting like 2 columns, it'll just pick the headings for those 2 columns to be X and Y. But when you have more than 2 columns, it doesn't know what you're graphing anymore, so it will not graph, it will not put a label on the y-axis. It'll still make whatever your first column is, the manipulated variable, it'll do that, but you'll have to fix the column stuff. So when we go to customize over here, okay, we're going to have to change a few things about this graph. And again, this is going to be something that you're going to have to do on Monday when you do your lab. All right, so we're going to go first to chart axis and titles, and it's got that really long, clunky title that we want to fix, and we'll just call it position versus time. That's a better title. Okay? And then I also have to put a label on my vertical axis. So I'll click where it said chart title before, and I'll pick vertical axis title. Okay, click in there. What's on that axis?
Cart position.
Position, yeah. In what?
Meters.
Meters. Okay, so I'm going to put both of those things in, position. And then I'm going to put a bracket. And put a little m inside the bracket. All right, now I've got position in meters. Okay, it's already built a legend, but it will probably move it, okay, once I get the best fit lines and ask for the equation. So just as a quick review, where do we do that?
Series.
Series. Okay, so we go to series, click on series, okay, and I usually make my points a little bit smaller, okay, just because I don't like the really big ones. Okay. It makes it look like every point is on the line, and I don't like that. And then I'm going to click on trend line. It draws 1 for each set of data. Okay. And then I'm going to put in the label field, use equation. Okay, so I get that graph. Okay, and yours should look exactly the same.
My computer is not loading. It's taking a
No.
long time.
Yeah, it still has an empty Google Sheets thingy.
Okay, so with these three sets of data, okay, on this position versus time graph, which is what our lab on Monday is going to be about, position versus time graphs, okay, we are seeing three carts that are traveling at constant velocities. Okay, how do I know their velocities are constant? Okay, because I told you. But by looking at the graph, how do I know that their velocity is constant? And let me tell you this extra piece of information. If something is traveling at a constant velocity, it changes its position by a constant amount every time interval. Are these doing that? How do we know that?
Because they're straight lines.
They're straight lines. Okay? If I can make a fairly straight line out of my points, and that's what Google does for us. My points don't necessarily show that, but they're close. Okay? They show that the object's position changes by the same amount every second. Okay? That means if I'm traveling at 5 meters per second, or let's say I'm cart number 2, the red line, I'm traveling at 2.01 meters per second. So every second, I will be 2.01 meters further from where I started. Okay, everybody all right with that idea? What's that? Yes. Okay, so these are all three of these carts are traveling at constant velocities. Which one is the fastest? The one with the greatest starts with S? Slope. Yeah, and speed. Because on this graph, because those are both the right answer, on this graph, the slope is the speed.
Let's go.
Okay, that's what I want to show you about this graph. Okay, if I'm solving for the slope, okay, that's m right here, right? Because these are all y. Whoop, I want the little lines. Okay, these are all y equals m, which is the slope, times x plus b, which is the y-intercept. Okay, now velocity as a formula is displacement divided by time. Okay? We haven't done this yet, but you calculate displacement as your change in position. We talked about that being the definition of it, but we've never actually calculated it. Okay? So, displacement is our change in position. We do that by taking our final position and subtracting our initial position. And then if I want to calculate velocity, I divide that by time. Okay? Still the same formula. All right? Now, on this graph, m, on this graph only, m represents the velocity of the cart. Okay? And here's why. If I manipulate this formula for m, I subtract b from both sides, and then I divide by x. That equals m. Does that formula look like this formula? Is it the same pattern?
Oh, yeah.
Okay. So y in this formula would be my final position. B, which is my y-intercept, my position at time 0, would be my initial position. X is time. That's where that formula that we've been using for a week comes from. V equals d over t calculates the slope of the line on a velocity, on a position versus time graph. Okay? Most of the formulas that we use are in some way, shape, or form derived from a graph. Okay? This is just the first example of one. Right? Does everyone follow the relationship between these two?
Yeah.
Okay, so that's one of the skills that we have to develop in physics, is to be able to analyze a graph and say, okay, this graph is showing me where the object is at various points in time, its position versus time, okay, and it's also going to allow me to calculate some other things. If I know where it is at certain points in time, I could calculate its displacement, because I could take its final position and subtract its initial position. Or I could also calculate its velocity, because I can get its change in position and divide it by the time, which would be the slope of the line. Okay? So sometimes you can get a question on a test that works like that. Okay, like for example, I did this to my physics 20s, okay, and I'll probably do it to you, okay? On their test, I gave them a graph that looked like this in the written response section of the test. And for 1 mark, I asked them, what is the velocity of cart 2? Why was that question only out of 1 mark?
Because it's like really easy, you just look at one number.
Right, I don't have to do anything. The velocity for cart 2 is 2.01 meters per second. The answer's right there. As long as I can recognize or analyze that the slope of this graph, this here, is the same as doing this. On this graph, y minus b is final position minus initial position divided by time. That calculates v. Okay, that's a recognition or an analysis thing. It doesn't involve me to do any calculating. I just have to recognize the number is there in front of me. So, spoiler alert, if a question is out of 1 mark, there's no work. Do you know how many people showed me 4 or 5 marks worth of work? About 1/3. Okay? So, there's a little thing to watch for. If a question, the written response question is only out of 1 mark, the answer is probably right in front of you. Okay? Don't do 4 marks worth of work for a 1 mark question. The flip is also true. Don't do 1 mark's worth of work for a 4 mark question, because then you probably did it wrong. Yeah? Okay. Okay, so that answers question number 1 then, for this graph. What's the velocity of each cart? On this graph, the velocity is represented by the slope of the line, because it tells me the rate at which I change my position. Okay? In the case of cart 1, that's 1.38 meters per second. For cart 2, it's 2.01 meters per second, and 3.39 meters per second for cart 3. Okay? Slope always tells us the rate at which y changes as a function of x, or y divided by x. Okay, everyone follow me there? So on every graph, the slope is going to be something different. Okay, on this graph it's velocity. On a velocity versus time graph, it's acceleration. On a graph of stock prices over time, it's the rate at which the stock changes its value per day or per week or whatever. Okay, if we're talking about like the mass of a person on a diet, okay, would that slope be positive or negative? Hopefully negative. I mean, if they're on a diet, they're probably trying to lose mass. Notice I didn't say weight, because they're different. Okay. Yeah, if I was looking at a graph of somebody on a diet, they would have mass in kilograms and probably time in weeks. Okay, and it would go like that. Okay, hopefully. Well, maybe not hopefully. It would depend on what the scale is. That's a terrible graph because there's no scale there. This could be a very unhealthy weight loss. Okay, or it could be a very, very slow weight loss. Okay, it all depends on what my scale is. But it would be negative because they would be decreasing. Is it okay for a graph to have a negative slope? Absolutely. Okay. In fact, I could have a position versus time graph that looks like this and goes down into the negatives. What does that mean? What's the car doing? Going backwards at a constant velocity. Okay, and so maybe this is a graph of someone who started in Calgary and went to High River, and 0 would be Okotoks. Okay, something like that, but they're traveling south, so their velocity would be negative. Okay. All right, I would like you guys to try questions 2 and 3. They're those y equals mx plus b manipulation type questions we're working on. Here's the other thing. 2 and 3, actually 1, 2, and 3, are basically the analysis for the lab on Monday. Okay, so try them now. We'll walk through them together and pay close attention to what we do. Okay? All right, so we already did number 1, okay, and we figured out that the slope of the line was the velocity for each cart, and we showed the manipulation for that, okay? Question number 2 wants to know the position of each cart after 12 seconds. So in terms of y equals mx plus b, what are they asking me to find?
Oh, why?
Why? How do I know that? What's on the y-axis? Position. So if they're asking me for position, I just look at what axis position is on, and I know I'm solving for that. So that means I don't even have to manipulate this equation. I just have to plug in what for x? 12. Okay? They want to know what is y when x is 12. Okay? On this graph, that is what is the position at 12 seconds. Okay? So we're going to take for cart number 1. Okay? So we'll do the manipulation here, and then we'll just, oh, actually, we don't have to manipulate, we just said that. Okay, so for the blue cart, that is going to mean 1.38, okay, times 12 seconds plus 9.52 times 10 to the minus 3. Now, just as a quick review here, if I have 9.52 times 10 to the power of minus 3, that means move the decimal 3 spots. Now the decimal is here, 0.00952, okay, is the number for B for that one. Okay, so for the blue cart, I really should have had that calculator fired up earlier. Okay, so we will have 1.38 times 12 plus 0.00952. Could I also just put that in scientific notation if I wanted to, like I do with the mole number, with Avogadro's number? Totally good. Okay, so the position of that cart is going to be 16.6 meters, and that's positive because it's going up. Okay. If I'm doing this for cart number 2, same thing. Okay, looking for y, that's going to be 2.01 times 12. So this is v times t, isn't it? Right? If I'm looking for y, I'm looking for a position, almost like a displacement. Okay, so this is v times t plus the initial position of the cart, which for this one is actually a negative number. Just means the y-intercept is below the x-axis a little tiny bit. Okay, so 2.01 times 12, and then we'll just subtract. What was it? Negative point, what was it, 0.5 something? 0.0524. Okay, so we have 24.07. So 24.1 meters. Okay, does it make sense that the red cart should have a higher position after 12 seconds? It does, because the red cart is going faster. So in the same amount of time, it should go further. All right, and then for the last one, okay, for the yellow carts, okay, we're going to have y equals 3.39, okay, times 12 plus 0.0381. All right, so we're looking at 40.7 meters. And that would also be a positive position. Okay, everybody all right with number 2? Okay. How many people have done number 3? Okay, let's have a look at number 3 then. All right, so on number 3, they want to know how long it will take. What am I looking for? Time, which is on the x-axis. All right, so that means right away I've got to figure out what my manipulation of this formula is going to be. All right, so if I'm trying to solve for x, what should I move first? B, it's not attached to x. So y minus b equals m times x, right? To move something, I do the opposite. I still want x by itself. What do I do with m? divide, because that's the opposite of multiply. What I do to one side, I do to the other, and now I've got my manipulation. Y minus b over m will give me x. All right, so now I've got to plug in my numbers for each one of the carts. So for the blue cart, okay, x is going to equal 1.3, oh, sorry, no. That's got to go on the bottom. Okay, is going to be 50 minus 0.00952, right, divided by 1.38. Now, this is something you have to be careful of. Don't put this all in a line on your calculator.
Well, if you use brackets.
If you use brackets, it's fine. But don't put it all in a line without brackets, or your calculator will do order of operations, which is it'll divide 0.00952 by 1.38 and then subtract that from 50. Is that the same as subtracting 0.00952 from 50 and then dividing that by 1.38?
No.
It is definitely not the same thing. Okay, so you've got to watch your order of operations and outsmart your calculator. Okay, so that's going to take cart number 1 36.2 seconds. Okay, for cart number 2, okay, same calculation. X is going to be this time 50 minus negative 0.0524 divided by 2.01. Should this number be bigger or smaller than the last one? Smaller, it's faster. Okay, it should take less time to get to 50 meters. All right, so 50, and we're just going to go plus 0.0524, and then divide that by 2.01. Okay, notice I did those calculations separately. That's the other thing you can do instead of brackets. Right, 24.9 seconds. Okay, and then for the yellow car, X is going to be 50 minus 0.0381 divided by 3.39. This should be the smallest of the times we have calculated thus far because it is the fastest of the carts. All right, 14.7 seconds. Okay, everybody with me there? What we just did there is the analysis for the lab on Monday. Okay, I will ask you, what are the velocities of your carts? Calculate how far your carts would go after this amount of time, or calculate how long it would take them to go this far. Okay, so exactly what we did there is what you're going to be asked to do for the analysis on Monday. Alex?
Do you want the numbers to the 10th place, or can we go into the 100th?
We haven't talked about significant digits yet, so when I do, I'll answer that question better. For now, I don't care.
Okay.
But once we do significant digits, then it'll always be a rule to follow. Okay, it's not a hard rule, by the way. But I'd probably make that sound really difficult, but it's not. Okay. All right, you know what? We're going to stop there. So, if you can, please make sure you sign out. Shut it down, wait for all the lights to go off, close the lid, put it back in the car.